Found a few boxes of these. We used to race these back in the day. Yeah, that's an AFX there. We modified the heck out of those until I had a hard time racing the Tyco Pros. They came out with the G Plus, and those are a little bit faster. Man, those tires have turned to dust. And then the riggings with the brass chassis and the can motor, those are pretty quick too. So those older cars don't work that well with these Super G Plus controllers. Squeeze the trigger and nothing happens, and they just kind of take off like that. Must be the color. Our controllers in the 70s were yellow. I read though that the Mega G Plus cars don't like these either. I had a broken one, decided I'd open it up. It looks like it's a high resistance wire wrapped around a tube. Pull the trigger, the wiper moves closer to the voltage source. Less resistance, more current. It's a variable resistor. So why can't I just use a potentiometer to fix my broken one? If I just use two wires, it's a variable resistor just in a circle rather than a straight line. If I'm running a 15 volt power supply, my car is drawing 0.25 amps. That's 3.75 watts. That high resistance wire can handle the watts. I mean, they use high resistance wire in 500 watt blow dryers, right, and space heaters. But that potentiometer is only rated for about a quarter watt. It might burn up if you try to stick it in your controller and race a car with it. At least mine did. So I got to thinking, what if we take the potentiometer and connect it to a MOSFET? I mean, let the MOSFETs do the heavy lifting, and the potentiometer just supplies the voltage. So let's hook them together and see what we can come up with. Well, I see two problems. In order to vary our input, this thing is configured as something called a source follower, so we really never get full voltage, kind of like restrictor plate racing. Cars all clumped together going the same speed. I miss the good old days when Awesome Bill would lap the field like they're standing still. Second problem, this is wired as a potentiometer, not a variable resistor. 1, 2, 3 wires, so I would need to rewire my track. That's not a problem, I wanted to do that anyway. I put one together and it does work. A little sluggish with the older AFX, faster with the newer car. Certainly a cheap fix for a broken control. I guess I could turn up the voltage to offset the source follower issue. I wish I'd left a broken wiper in place, so I like the feel of resistance. This is like squeezing air. Remember when you used to clip the playing cards against the spokes of your bicycle? That nice sound and feel, that I saw this advertised. Replacement trigger for brushed DC drill motor, brake, variable speed, and full power. That sounds like a slot car controller. The first thing you need to know, that black wire right there is not ground. If you plug that into your brand new rewired track, you'll short it out. At least I did. Underneath that heatsink is an N-channel MOSFET. So I could use that to drive a P-channel MOSFET. Then I could get back to my common ground, right? And it works amazingly well. The problem is the variable speed wiper range is only about 3 millimeters, and that ain't much wiggle room. Too easy to accidentally pull too hard and fly off the track. I stumbled across this article. It's by Crutschow. That guy's a pro. He uses a little chip 393 to create an oscillator, and he feeds that back into the same chip to create pulse width modulation, PWM, with a 0 to 100% duty cycle. There's the basic circuit. I had to modify it a bit. I only have 90 degrees of wiggle room for my trigger, right? A 10K pot in the basic circuit goes from 0 to 100% duty cycle in 270 degrees. I need a 90 degree wiper. What to do? I plugged in a 50K potentiometer. That got me down to 180 degrees. Tried a 100K potentiometer, 110 degrees. 250K, 90 degrees. Mod 2, frequency. So what is frequency? Frequency is defined as the cycles per time period. So 1 hertz is 1 cycle per second. Crutzchow's circuit is about 1 kilohertz. What's the ideal frequency for a slot car? I don't know. We could ask Kenneth. So I was reading various slot car forums, DC motor forums, circuit forums. The sweet spot seems to be somewhere between 100 hertz and 20,000 hertz, or 20 kilohertz. Well, that narrows it down. I'm sure it depends on the characteristics of the motor. So I combined a 15 nanofarad capacitor with a 100K pot in my circuit, so I could vary the frequency from a couple of hundred hertz to a few kilohertz. Still not quite sure how to identify the ideal frequency. You know, maybe it's like adjusting the high-speed needle on a 2-stroke carb. You lean it out until your maximum RPMs, then you back it down until you're 4-stroke and sound like a Harley. Then you lean it out a bit till you hit the sweet spot. Something like that, maybe. I guess. Maybe. Who knows? Anyway, that's the frequency potentiometer. I added a 50K pot to the low side of the 250K wiper so I could adjust the starting voltage. Why? 2 reasons. When I press the trigger on the 250K wiper pot, it needs to be set right at 0 duty cycle, so I get to use my full 90 degree range. If I'm off a little bit, rather than pulling the trigger off and trying to position it over and over again, I can just adjust the starting voltage. The other reason is some cars are sluggish out the gate, like this one. Oh my goodness, this thing out the gate is slower than my dishwasher. I figure if I give it a little more starting juice, it gets off the line quicker. I think turning the frequency up for those cars might help too. I was reading that model trains need a higher frequency to start because they are heavy. Maybe this car has been drinking too many mellow yellows. This is the 50K pot I added. You can see it at the bottom of the circuit diagram. Let's look at the oscilloscope. First, 250K wiper pot going from 0 to 100% duty cycle. And then we'll look at the frequency next. And you can see it going from several hundred hertz to several kilohertz back and forth. And we can also look at the starting voltage. It goes up and down a little bit. This one's a little bit hard to see on the oscilloscope. Expo. If you've ever flown RC airplanes, you know, if your plane's a little too twitchy, you have dumb thumbs like I do, you can add a little expo and it slows the aileron response. So when you turn the plane, you're not suddenly flying upside down. The 250K wiper has a linear response. Now, how can I make that a logarithmic response? I ran across this article. It looks like if I add a resistor between the ground and the wiper, it creates a curve. So if I add a 200K variable resistor, I think I can adjust the curve and smooth out the acceleration, I think. It might be enough just to vary the frequency and starting voltage. But let's plug it in and see what the oscilloscope shows. We'll set the 250K wiper at about 20% duty cycle to start, and then we can, so it looks like it drops from the 20% to nothing. As I turn it up, it takes off pretty quickly. I don't know what I'm doing here. I'm not sure I'm doing anything particularly useful. I think I might just, I think I might just leave that one out for now. And I guess I'm done, right? Not hardly. Can't sink much current with this circuit. Certainly can't fire up a race car. I need to add a 4-barrel polycarb and some nitro. This is the power circuit. 547 buffer and a P MOSFET. So we can plug in the PWM and we're off to the races. There's our 250K wiper pot. And we'll vary the starting voltage. Now let's vary the frequency. I could stop here, but where are the brakes? Where's the full power circuit? I think we have more work to do. I watched this by Afrotech Mods, and the light bulb came on. I can use a second 393 to do something when the wiper voltage goes high or when the wiper voltage goes low. So what? Well, if it gets up to a set voltage, I can have it switch to full power. Inversely, that's an important word when you speak of comparators. If it goes down to a set voltage, I can switch on the brakes. How? Well, I could use transistors, but I wanted to simplify my life. Relays. Relays have a normally closed and a normally open contact. Energizing the coil in the relay switches power from the normally closed to the normally open contact. So if I hook together two relays, I run the PWM through the relays in the normally closed position. When I energize one relay, it switches from PWM to full power. Inversely, there's that word again, when I energize the other relay, it switches from PWM to ground, shorting out the motor. So here's the relay circuit. I need to be able to adjust the voltage to switch to full power, and I need to be able to adjust the voltage for brakes. How? By replacing the resistors with potentiometers wired as variable resistors. When I adjust the pots, how am I going to be able to tell what I'm doing? LEDs. Red for brakes, that's obvious. Blue for full power. Why blue? Cops, pull over, you're speeding. One more thing to try. Dynamic braking. What happens when we short the motor to ground? The motor acts as a generator and we get a power surge the other way. What if we remove the ground wire and add a potentiometer between the relay and the ground? We can control the surge. All the potentiometers until now are in the 5-volt circuit. This one's in a 15-volt circuit, so I used a more robust potentiometer wired as a variable resistor. Let's crank it up and fire up the motor, put on the brake, and there's no voltage spike. Now let's turn it all the way back down, fire up the motor again, turn on the brake, and there's your voltage spike again. So let's review our full circuit. There's our power supply going to our 5-volt voltage regulator, which feeds our PWM circuit, which then feeds our power circuit and our comparator circuit for the brakes and full power override. There's our relay circuit and our LEDs, and there's the motor. I think a voltmeter is worth 1,000 words, so if the light bulb hasn't come on yet, maybe it will now. I've first connected that to our 250K wiper potentiometer, and you can see the voltage going up and down. It doesn't quite make it to 5 volts because we have a resistor on top of the voltage divider circuit. So notice our brake is off at 1.88 volts. If we turn the voltage down, our brake comes on. Now let's move the voltmeter to the brake circuit itself and see where it's set. It's set at 1.72 volts for the brake to come on. We can dial that up or we can dial it down. So now let's move our voltmeter to the full power circuit. And it looks like it's set to switch from PWM to full power at 3.12 volts. We can adjust that down or we can adjust it up. So now let's move our voltmeter back to our 250K wiper pot and let's turn the voltage up. When we get to about 1.72 volts, the brake should go off. There it went. Dial it back down, it goes on, off. Now let's turn the voltage up and see where our full power override kicks in. I think it's around 3.12 volts where it switches to full power. So let's build a controller. First thing you'll notice is that I used a 339 chip rather than two 393s, just saved a little bit of space. Same concept, there's a P MOSFET, and on the other side of the heat sink is my 5 volt voltage regulator. And then I have potentiometers for starting voltage, brake, and full power. And this is our 250K wiper pot. And our relays are in the handle. I use power pole connectors. Those are quite handy. And ground a flat on the potentiometer stem and tapped a set screw. Use some thread locker. And my trigger has a full 90-degree turn. For this controller I included starting voltage adjustment, brake adjustment, and full power adjustment. I did not include adjustable frequency though. That would have been cool. I kind of wish I had. I also did not include dynamic braking. I do have a flyback diode across the motor which may serve that purpose. When I build my next controller I may use a project box so I'll have room for all the potentiometers. Alright, let's take it to the track. 3 different cars, AFX, the Mellow Yellow, and whoa, what do we have here? Mega G Plus. So first we'll start with AFX. I'm going to dial all the dials down so you're just working on pulse width modulation. And I'm going very slowly because this thing fishtails all over the track, and I don't know how in the world we race these things back in the day. So I'm going to add a little brake to it, add a little starting voltage and brake. And now we're going to add a full power overload. This track is so short it's really hard to even use that feature, but it would be great with long straightaways. Alright, now let's try the Mellow Yellow car. First we're going to use the 60 ohm controller. And we get around the track okay with that. Now let's dial all the dials down so we're just on PWM. Now let's add a little starting voltage where it's almost going by itself. See that? Dial it back down, add a little brake, and let's go around again. See if we can get off the line a little quicker. Now we're going to add our full power override. Now let's try the Mega G Plus first with the 60 ohm controller, and this is not pleasant. You barely touch it and it goes, so you really don't have much control. Now let's dial all the dials down and just run it on PWM. Really a smooth car. Loads the track nicely too. Alright, let's add a little starting voltage where it just almost takes off by itself, and dial it back down a little, and then some brake. And now we're going to add full power override. That car's a lot of fun. So I guess you need a controller that fits your car, or you can invest in a controller that adjusts to the car. You can build your own. Now if I can just get this lap counter to work. Might have to build my own.